We talk about energy all the time. Having energy, saving energy, using energy. But what if I told you that the physicists who dedicate their entire lives to studying it don't actually know what it is? Well, that's the incredible mystery we're diving into. We all learn this one in high school science class, right? It's the classic go-to definition. Energy is what makes stuff happen. It's the juice you need to push something or lift it or just heat it up. Seems pretty simple. Case closed, right? Well, not so fast. Then you stumble across this bombshell from Richard Feynman, one of the sharpest minds in physics history. He's basically telling us that this simple idea is actually one of the biggest, deepest unknowns in all of science. So, what on earth did he mean? How can something so basic to physics be a total mystery? Let's dig in. Okay, so to really get what Feynman was talking about, you have to understand that our concept of energy wasn't just, discovered one afternoon. Nope. It was pieced together bit by bit over centuries. And that long, winding journey created some interesting complications. It all started way back in the 17th century with this idea of a living force. Then, in 1802, a guy named Thomas Young finally gave it the name we use today, energy. But it took until the mid-1800s for Helmholtz to connect all the dots and show that the force in motion, the heat in a fire, the spark of electricity, they were all just different faces of the same conserved thing. And right there, that's the core of the problem. Because as physics got bigger and more complicated, every new field kind of came up with its own way of thinking about energy. It was always the same thing that was being saved or conserved, but what that thing was seemed to totally change based on which physicist you were talking to. To really see what I mean, let's go on a little tour, a lightning round through 4 different branches of physics. And as we go, just pay attention to how the fundamental idea of what energy actually is keeps shifting. First stop, classical mechanics. Isaac Newton's world of falling apples and billiard balls. In this world, energy is exactly what you think it is. It's the ability to do work, the energy of motion plus the energy of position. Simple, clean, you can almost feel it in your hands. But then we jump over to thermodynamics, the physics of heat and engines. And suddenly, energy isn't just about pushing and pulling anymore. It's an internal quality of a system, like the jiggling of atoms in a hot gas. It's this abstract property that describes the state of the whole system, a totally different flavor. And this is where it gets really wild. With electromagnetism, James Clerk Maxwell shows us something that's just mind-bending. Energy isn't just in things. It can exist all by itself, in totally empty space, stored in these invisible electric and magnetic fields. A beam of light is literally energy traveling through a vacuum. The energy isn't in a particle, it is the wave in the field. And finally, just when you think you've got it figured out, Albert Einstein walks in and completely redefines the game again. In relativity, energy becomes something even more bizarre. It's a component of the very geometry of spacetime. And of course, this is where we get the big one, E equals mc squared, the revelation that mass is nothing more than a super-condensed form of energy. So do you see the problem now? We've got 4 totally valid but completely different ways of describing energy. Is it a capacity to do work, an internal state? Is it something stored in empty fields? Or is it a feature of space-time geometry? Which one is it, really? This is where the story takes this beautiful, elegant turn. The answer to this puzzle, it turns out, isn't about picking one definition over the others. It comes from a much deeper, much more profound idea that links energy to the fundamental rules of the universe itself. And the hero of our story is a mathematician named Emmy Noether. In 1918, she came up with a theorem that is, and I'm not exaggerating, one of the most beautiful and powerful ideas in all of physics. She figured out that things like the conservation of energy aren't just random rules. They are the direct, unavoidable consequences of symmetries in our universe. So what kind of symmetry gives us energy conservation? It's something called time translation symmetry. Now, that sounds super fancy, but the idea behind it is incredibly simple. It just means the laws of physics don't change over time. An experiment you do today will give you the exact same result if you do it next year. The rules of the game are constant. What Noether's theorem does is it creates these perfect pairings. Look at this. If the laws of physics are the same everywhere, here or on Mars, then momentum has to be conserved. If the laws are the same no matter which direction you're facing, then angular momentum is conserved. And here's the big one for us. Because the laws of physics are the same through time, there has to be some quantity that is conserved, and we call that quantity energy. And that is the incredible answer to Feynman's puzzle. Energy isn't some kind of stuff. It's not a fluid, it's not a substance. It's something much more abstract. It's the number in the equations that has to, mathematically, stay the same, simply because the universe's rules don't have an expiration date. But you know how it goes in science. This absolutely beautiful solution cracked open a door to even bigger, even weirder mysteries. Because this new definition of energy, as a consequence of timeless laws, runs into some serious trouble at the cutting edge of physics. So, mystery number 1, gravity. It turns out, in Einstein's theory of general relativity, you can't actually point to a spot and say, this is how much energy the gravitational field has. And if you can't define the energy of gravity, and space itself is expanding, then the total energy of the whole universe doesn't seem to be conserved. Light waves lose energy as they cross the expanding cosmos, and that energy, well, it just seems to vanish. But honestly, that problem is nothing compared to the second mystery. This is the big one. It's all about the energy of absolutely nothing, of pure empty vacuum. So here's the standoff. In one corner, you have quantum field theory, our best description of particles. It predicts that empty space should be absolutely buzzing with a colossal amount of energy. But in the other corner, you have general relativity, our best description of gravity. It looks out at the cosmos and sees that the energy of empty space is incredibly tiny, almost zero. So just how far apart are these two ideas? Well, our quantum theory predicts a value for the energy of space that is bigger than what we actually see by a factor of 1 followed by 120 zeros. I mean, that's not just getting the answer wrong, that's being in a completely different reality from the right answer. Yeah, it is a failure so spectacular, so staggeringly huge, that scientists have called it the worst theoretical prediction in the history of physics. It's a giant flashing sign that our two most successful theories of the universe fundamentally disagree on what energy even is. So think about where we've been. We started with a simple definition from a textbook. We traveled through history to find this beautiful, profound idea based on symmetry, only to wind up right at the edge of human knowledge, staring at one of the deepest paradoxes scientists have ever faced. And that leaves us right back where we started, but with a much, much deeper question. Is energy some kind of fundamental stuff that makes up reality? Or is it something more ghostly, just the mathematical shadow cast by the fact that the laws of our universe are eternal? Right now, nobody knows. The answer is still out there.